Okie dokie. Hello everyone. I'm going to continue to study 3D graphics, and one thing what I realized. Hello Ilya. The ergonomics of the writing the 3D graphics code is kind of messed up. One of the reasons is you have to use 4 files. One is for header file, one is for source file, and there is 2 files for vertex shaders and fragment shaders. And I'm wondering if I should rename them. So if I order them alphabetically, they would be like clumped together, right? Like hello triangle, for example, or hello triangle, and right now they are spread out, and it's not very ergonomic. So I was doing it by ordering them by time, modification time. Still not very reliable, and order always time changing. So I'm going to spend some time and do renaming. So I think I would do it like this maybe. Right, and so rename them like this, and it's gonna look like a bit better, right? So we would have like a hello triangle, shaders tutorial, textures, transformations. So I think it's way better. So let's update makefile. So makefile would be fs vs fs vs vs fs fs vs vs okay. And now I think what I need to do example cubes. Yeah, this is okay. Anyways, I need to look up for load program. Oh my. And update here. Okay. So let me, just to be sure, do more or less clean build. I'm going to delete. Oh, wait a second, I forgot to delete beans, so let's do again. Okay. Okay, so this is transform is working. Huh. Redefinition of textures. Um, hmm. Oh, main.cpp. In transformation.hpp. Revert. I think. No. Oh, it's disappeared. Cool. Let's go through all hello triangle. I don't think this is the color. Hello triangle. Fragment shader. Oh, it is. Okay. It is the color. No. Gel frag color. It should be orange. Let's look at our ones. Hello triangle shaders tutorial. Oh, this one is V color 0. Okay. Shaders tutorial V color 1. 1 0 1 Still failing. V color 0. Where is it? Ah. V color 0. Okay. So I think I'm starting getting order in all this madness. So I kind of understanding where things are going. So let's see shaders tutorial again. Fragment shader, effrag color. But triangle doesn't work for some reason. So this is the hello triangle shaders tutorial, fragment shader. Oh no. GL frag color. What the heck? I just said things are making sense and things are not making sense now. Hello triangle, vertex shader. So it should be orange. And it's not orange. Oh. Hello triangle, hello triangle. There is not too much. Main. It's black. Where this black is coming from? Gel frag color. Let's see. I do not understand. Fragment shader. It's simple it's very simple. It's still black. Let's copy paste this one. Still black. Undefined variable vColor1. Undefined variable vColor1. What? vColor1. Ah, typo. So let's me uncomment this part. Comment out this. It's red, right? And we want orange. So let's me add this. Still red. Let me, just to be sure, let me put like a lot of blue. Yeah, it's still red. So compiled, fragment shader. It doesn't make sense. I just, like a literally second, I said, oh, things are making sense now. Stop making sense. Oh, it's red. Where this red is coming from? hello triangle, hello triangle, fragment shader. Where is input vcolor 1, input vcolor, everything exactly same. This is same, this is same, this is same, and I'm clearly passing blue. Let's look at the compiled shader. Maybe it will give bin triangle fragment shader. So gel frag color v color 1 varying v color 1. So this would go to BGFX frag color, and this is the out. This is varying. Position v color 1. Gel position. BGFX. So let me see. There is a bunch of shader. So where are shaders? Examples, bindings, examples. Where are shaders? Runtime shaders. Okay. Let's look at some simple shader. Cubes. Oh, it did not say version. That's interesting. It's not specifying version. Profile. Let me see if we have a profile anywhere. There is no profile. Oh, it's not specifying. So maybe this is the problem. Maybe I should not specify profile. So if I remove profile, so delete beans. It wants profile. Shader profile must be specified. Defaults to GLSL. GLSL. Unknown profile GLSL. Disasem. It's not setting the VS flags. It's dash P. This is why it did not show up in the search. Okay, so 120. Uh, one 430. There is a 430. One to zero. One to zero. 430. So there is option of 430. And 430 is for compute shader. So I guess I need to do 120. So let's do make file. Okay, let's delete bin directory. Okay. Not much in function to call texture. To call mix. Interesting. So let's postpone this thing. So this is transformation. Fragment shader. Let's see if triangle get the color. It looks orange or it's still red. Okay, it became smaller. And V color. Okay. Triangle. No, it should be not red. Yeah. What's going on? Waiting. V color. Fragment shader, vertex shader. Unwanted semicolon somewhere, right? A position. V color 1. Temp var. What? It did something fancy with temp var. Ah. vec4 1 0 0 like 1 0, let's 1. What's going on? Where it's getting this red color? Fragment shader. This fragment shader is like as simple as, I don't know. It should be that color, not red. There's not too much wiggle room. It just simple as 1 2 3. Simpler. Okay, one thing, main. It is hello triangle. Right? Hello triangle dot cpp. It's loading hello triangle. Hello triangle. Oh my god. I found the bug. What is it? Shaders tutorial load program. So it should VSFS. So in this order. Only 40 minutes spent. Not big deal. Okay, so hello triangle. We just put the color here. Remove this stuff. And also hello triangle. So this is like this. We don't need this thing. We don't need this thing. Okay, let's change the color a bit. Hello triangle. So let's make it orange as it used to be. 5 2. It's kind of orange. Okay, and now make file. I guess I'll get back to 430. So textures. So I can uncomment this part and transformations. Uncomment this part. Okay. There is just the names. Shaders tutorial. Why is marked as deleted? Hello triangle. Ah. Yeah, let's put this original. Okay, and first shader tutorial fs. So what the difference? Ah, so this is vcolor 0 and this is vcolor 1. Okay. Okay, let's go from beginning. Let's see weighting. Did I change any weighting? No, weighting did not change, right? Okay. So let's go from beginning. Main file. Hello triangle shaders tutorial. Shaders tutorial. Okay, looks good. Textures. Okay, looks good. Then I did this thing off the stream. Transformations. It did not take too much time for me to implement transformations. Probably 15 minutes, maybe half an hour. Okay, this is working. And now let's go through the book. Oh, you know... yeah, I was thinking maybe I should make all these classes... Oh, the results example cubes. But example cubes should work just as is. Example cubes, because it's reusing shaders. Yeah. Okay, let's go through the book. So we are now doing 3D. Chapter 9. Going 3D. Coordinate system. I don't know, do they have any examples in the coordinate system? Or just talking? There is some samples. Okay. Okay, so we are going to render the cube. Nice, nice, nice. Okay, z buffer, and put more cubes. It's cool. Okay, so, and the chapter name is coordinate system. Coordinate system. Okay. Coordinate system. Oh. Okay. And then let's go to main. Include coordinate system .hpp and put it here. Okay.
In the last chapter, we learned how we can use matrices to our advantage by transforming all vertices with transformation matrices. OpenGL expects all the vertices that we want to become visible to be in normalized device coordinates after each vertex shader run. That is, the x, y, and z coordinates of each vertex should be between -1.0 and 1.0. Coordinates outside this range will not be visible. What we usually do is specify the coordinates in a range or space we determine ourselves, and in the vertex shader, transform these coordinates to normalized device coordinates NDC. These NDC are then given to the rasterizer to transform them to 2D coordinates /pixels on your screen. Transforming coordinates to NDC is usually accomplished in a step-by-step fashion where we transform an object's vertices to several coordinate systems before finally transforming them to NDC. The advantage of transforming them to several intermediate coordinate systems is that some operations /calculations are easier in certain coordinate systems, as will soon become apparent. There are a total of 5 different coordinate systems that are of importance to us. Local space or object space, world space, view space, or eye space, clip space, screen space. Those are all a different state at which our vertices will be transformed in before finally ending up as fragments. You're probably quite confused by now by what a space or coordinate system actually is, so we'll explain them in a more high-level fashion, first by showing the total picture and what each specific space represents. To transform the coordinates from one space to the next coordinate space, we'll use several transformation matrices, of which the most important are the model, view, and projection matrix. Our vertex coordinates first start in local space as local coordinates and are then further processed to world coordinates, view coordinates, clip coordinates, and eventually end up as screen coordinates. The following image displays the process and shows what each transformation does.
Local space world space, view space, clip space, screen space. Model matrix, matrix, view matrix, projection matrix, viewport transform.
Local coordinates are the coordinates of your object relative to its local origin. They're the coordinates your object begins in. The next step is to transform the local coordinates to world space coordinates, which are coordinates in respect of a larger world. These coordinates are relative to some global origin of the world, together with many other objects also placed relative to this world's origin. Next, we transform the world coordinates to view space coordinates in such a way that each coordinate is as seen from the camera or viewer's point of view. After the coordinates are in view space, we want to project them to clip coordinates. Clip coordinates are processed to the -1.0 and 1.0 range and determine which vertices will end up on the screen. Projection to clip space coordinates can add perspective if using perspective projection. And lastly, we transform the clip coordinates to screen coordinates in a process we call viewport transform that transforms the coordinates from -1.0 and 1.0 to the coordinate range defined by GL viewport. The resultant coordinates are then sent to the rasterizer to turn them into fragments. You probably got a slight idea what each individual space is used for. The reason we're transforming our vertices into all these different spaces is that some operations make more sense or are easier to use in certain coordinate systems. For example, when modifying your object, it makes most sense to do this in local space, while calculating certain operations on the object with respect to the position of other objects makes most sense in world coordinates, and so on. If we want, we could define one transformation matrix that goes from local space to clip space all in one go, but that leaves us with less flexibility. We'll discuss each coordinate system in more detail below. Local space is the coordinate space that is local to your object, i.e. where your object begins in. Imagine that you've created your cube in a modeling software package like Blender. The origin of your cube is probably at 0, 0, 0, even though your cube may end up at a different location in your final application. Probably all the models you've created all have 0, 0, 0 as their initial position. All the vertices of your model are therefore in local space. They are all local to your object. The vertices of the container we've been using were specified as coordinates between -0.5 and 0.5 with 0.0 as its origin. These are local coordinates. If we would import all our objects directly in the application, they would probably all be somewhere positioned inside each other at the world's origin of 0, 0, 0, which is not what we want. We want to define a position for each object to position them inside a larger world. The coordinates in world space are exactly what they sound like, the coordinates of all your vertices relative to a game world. This is the coordinate space where you want your objects transformed to in such a way that they're all scattered around the place, preferably in a realistic fashion. The coordinates of your object are transformed from local to world space. This is accomplished with the model matrix.
Model matrix.
The model matrix is a transformation matrix that translates, scales, and slash or rotates your object to place it in the world at a location / orientation they belong to. Think of it as transforming a house by scaling it down. It was a bit too large in local space, translating it to a suburbia town, and rotating it a bit to the left on the y-axis so that it neatly fits with the neighboring houses. You could think of the matrix in the previous chapter to position the container all over the scene as a sort of model matrix as well. We transformed the local coordinates of the container to some different place in the scene / world. The view space is what people usually refer to as the camera of OpenGL. It is sometimes also known as camera space or eye space. The view space is the result of transforming your world space coordinates to coordinates that are in front of the user's view. The view space is thus the space as seen from the camera point of view. This is usually accomplished with a combination of translations and rotations. Translate / rotate the scene so that certain items are transformed to the front of the camera. These combined transformations are generally stored inside a view matrix that transformed world coordinates to view space. In the next chapter, we'll extensively discuss how to create such a view matrix to simulate a camera. At the end of each vertex shader run, OpenGL expects the coordinates to be within a specific range, and any coordinate that falls outside this range is clipped. Coordinates that are clipped are discarded, so the remaining coordinates will end up as fragments visible on your screen. This is also where clip space gets its name from, because specifying all the visible coordinates to be within the range -1.0 and 1.0 isn't really intuitive. We specify our own coordinate set to work in and convert those back to NDC as OpenGL expects them. To transform vertex coordinates from view to clip space, we define a so-called projection matrix that specifies a range of coordinates, e.g. -1000 and 1000 in each dimension. The projection matrix then transforms coordinates within this specified range to normalized device coordinates 1.0, 1.0. All coordinates outside this range will not be mapped between -1.0 and 1.0 and therefore be clipped. With this range we specified in the projection matrix, a coordinate of 1250, 500, 750 would not be visible, since the x-coordinate is out of range and thus gets converted to a coordinate higher than 1.0 in NDC and is therefore clipped. Note that if only a part of primitive, for example, a triangle is outside the Clinton volume OpenGL, we'll reconstruct the triangle as one or more triangles to fit inside the Clinton range.
Oh, really? Interesting.
This viewing box a projection matrix creates is called a frustum, and each coordinate that ends up inside this frustum will end up on the user's screen. The total process to convert coordinates within a specified range to NDC that can easily be mapped to 2D viewspace coordinates is called projection, since the projection matrix projects 3D coordinates to the easy map to 2D normalized device coordinates. Once all the vertices are transformed to clip space, a final operation called perspective division is performed where we divide the x, y, and z components of the position vectors by the vector's homogeneous w component. Perspective division is what transformed the 4D clip space coordinates to 3D normalized device coordinates. The step is performed automatically at the end of the vertex shader step. It is after this stage where the resultant coordinates are mapped to screen coordinates using the settings of GL viewport and turned into fragments. Projection matrix to transform view coordinates to clip coordinates usually takes two different forms, where each form defines its own unique fru. Frustum, we can either create an orthographic projection matrix or a perspective projection matrix. Orthographic projection. An orthographic projection matrix defined a cube-like frustum box that defined the clipping space where each vertex outside this box is clipped. When creating an orthographic projection matrix, we specify the width, height, and length of the visible frustum. All the coordinates inside this frustum will end up within the NDC range after transformed by its matrix, and thus won't be clipped. The frustum looks a bit like a container. The frustum defined the visible coordinates and is specified by a width, a height, and a near and far plane. Any coordinate in front of the near plane is clipped, and the same applies to coordinates behind the far plane. The orthographic frustum directly maps all coordinates inside the frustum to normalized device coordinates without any special side effects, since it won't touch the W component of the transform vector. If the W component remains equal to 1.0, perspective division won't change the coordinates. To create an orthographic projection matrix, we make use of GLM's built-in function glm::ortho. The first two parameters specify the left and right coordinate of the frustum, and the third and fourth parameter specify the bottom and top part of the frustum. With those 4 points, we've defined the size of the near and far planes, and the fifth and sixth parameter then define the distances between the near and far plane. This specific projection matrix transforms all coordinates between these x, y, and z range values to normalized device coordinates. An orthographic projection matrix directly maps coordinates to the 2D plane that is your screen, but in reality, a direct projection produces unrealistic results since the projection doesn't take perspective into account. That is something the perspective projection matrix fixes for us. Perspective projection. If you ever were to enjoy the graphics, the real life has to offer, you'll notice that objects that are farther away appear much smaller. This weird effect is something we call perspective. Perspective is especially noticeable when looking down the end of an infinite motorway or railway, as seen in the following image. As you can see, due to perspective the lines seem to coincide at a far enough distance. This is exactly the effect perspective projection tries to mimic, and it does so using a perspective projection matrix. The projection matrix maps a given frustum range to clip space, but also manipulates the W value of each vertex coordinate in such a way that the further away a vertex coordinate is from the viewer, the higher this W component becomes. Once the coordinates are transformed to clip space, they are in the range W to W. Anything outside this range is clipped. OpenGL requires that the visible coordinates fall between the range -1.0 and 1.0 as the final vertex shader output. Thus, once the coordinates are in clip space, perspective division is applied to the clip space coordinates. Each component of the vertex coordinate is divided by its W component, giving smaller vertex coordinates the further away a vertex is from the viewer. This is another reason why the W component is important, since it helps us with perspective projection. The resultant coordinates are then in normalized device space. If you're interested to figure out how the orthographic and perspective projection matrices are actually calculated and aren't too scared of the mathematics, I can recommend this excellent article by Songho. A perspective projection matrix can be created in GLM as follows. What GLM::perspective does is again create a large frustum that defines the visible space. Anything outside the frustum will not end up in the clip space volume and will thus become clipped. The perspective frustum can be visualized as a non-uniformly shaped box from where each coordinate inside this box will be mapped to a point in clip space. An image of a perspective frustum is seen below. Its first parameter defined the FA value that stands for field of view and sets how large the view space is. For a realistic view, it is usually set to 45 degrees, but for more Doom-style results, you could set it to a higher value. The second parameter sets the aspect ratio, which is calculated by dividing the viewport's width by its height. The third and fourth parameter set the near and far plane of the frustum. We usually set the near distance to 0.1 and the far distance to 100.0. All the vertices between the near and far plane and inside the frustum will be rendered. Whenever the near value of your perspective matrix is set too high, like 10.0, OpenGL will clip all coordinates close to the camera between 0.0 and 10.0, which can give a visual result you maybe have seen before in video games, where you could see through certain objects when moving uncomfortably close to them. When using orthographic projection, each of the vertex coordinates are directly mapped to clip space without any fancy perspective division. It still does perspective division, but the W component is not manipulated, it stays 1 and thus has no effect. Because the orthographic projection doesn't use perspective projection, objects farther away do not seem smaller, which produces a weird visual output. For this reason, the orthographic projection is mainly used for 2D renderings and for some architectural or engineering applications where we'd rather not have vertices distorted by perspective. Applications like Blender that are used for 3D modeling sometimes use orthographic projection for modeling because it more accurately depicts each object's dimensions. Below, you'll see a comparison of both projection methods in Blender. You can see that with perspective projection, the vertices farther away appear much smaller, while in orthographic projection, each vertex has the same distance to the user. Putting it all together, we create a transformation matrix for each of the aforementioned steps: model, view, and projection matrix. A vertex coordinate is then transformed to clip coordinates as follows.
Model, view, projection.
Note that the order of matrix multiplication is reversed. Remember that we need to read matrix multiplication from right to left. The resulting vertex should then be assigned to GL position in the vertex shader, and OpenGL will then automatically perform perspective division and clipping. And then, the output of the vertex shader requires the coordinates to be in clip space, which is what we just did with the transformation matrices. OpenGL then performed perspective division on the clip space coordinates to transform them to normalized device coordinates. OpenGL then uses the parameters from GL viewport to map the normalized device coordinates to screen coordinates, where each coordinate corresponds to a point on your screen, in our case, 800x600 screen. This process is called the viewport transform. This is a difficult topic to understand, so if you're still not exactly sure about what each space is used for, you don't have to worry. Below, you'll see how we can actually put these coordinate spaces to good use, and enough examples will follow in the upcoming chapters. Going 3D now, that we know how to transform 3D coordinates to 2D coordinates, we can start rendering real 3D objects instead of the lame 2D plane we've been showing so far.
Lame.
To start drawing in 3D, we'll first create a model matrix. The model matrix consists of translations, scaling, and slash or rotations we'd like to apply to transform all objects' vertices to the global world space. Let's transform our plane a bit by rotating it on the x-axis so it looks like it's laying on the floor. The model matrix then looks like this.
Okay. I'm wondering why I put this thing here. I don't know. Model. Model rotate around X vertex.
By multiplying the vertex coordinates with this model matrix, we're transforming the vertex coordinates to world coordinates. Our plane that is slightly on the floor thus represents the plane in the global world. Next, we need to create a view matrix. We want to move slightly backwards in the scene, so the object becomes visible when in world space we're located at the origin 0, 0, 0. To move around the scene, think about the following. Move a camera backwards is the same as moving the entire scene forward. That is exactly what a view matrix does. We move the entire scene around inverse to where we want the camera to move, because we want to move backwards, and since OpenGL is a right-handed system, we have to move in the positive z-axis. We do this by translating the scene toward the negative z-axis. This gives the impression that we are moving backwards. Right-handed system by convention. OpenGL is a right-handed system. What this basically says is that the positive x-axis is to your right, the positive y-axis is up, and the positive z-axis is backwards. Think of your screen being the center of the three axes, and the positive z-axis going through your screen towards you. The axes are drawn as follows. To understand why it's called right-handed, do the following. Stretch your right arm along the positive y-axis with your hand up top. Let your thumb point to the right. Let your pointing finger point up. Now bend your middle finger downwards 90 degrees. If you did things right, your thumb should point towards the positive x-axis, the pointing finger towards the positive y-axis, and your middle finger towards the positive z-axis. If you were to do this with your left arm, you would see the z-axis is reversed. This is known as a left-handed system and is commonly used by DirectX. Note that in normalized device coordinates, OpenGL actually uses a left-handed system. The projection matrix switches the handedness. We'll discuss how to move around the scene in more detail in the next chapter. For now, the view matrix looks like this.
Translate. We move backwards. On z-axis. They actually because I would probably want to have, I'm fan of z up, you know, z is this direction, and have right-handed, so like a same thing as a blender. So I want to have a blender system, so I would not need to bend my brain and try to figure out what is what. So anyways, we will figure out this thing later on, but right now let's just stick with the tutorial.
The last thing we need to define is the projection matrix. We want to use perspective projection for our scene, so we'll declare the projection matrix like this.
Yeah, I know I can change it, and I just do not want to do it right now. I just want to stick with the tutorial, but then I would start doing something for myself. I would set the Z up and use right-handed system. What was my favorite class in college? I don't think I enjoyed anything in the college. It was miserable. Yeah, I don't think I enjoyed anything. Maybe physics. Physics was a bit fine. Yeah, physics was kind of okay. After physics, I do not know. Maybe math was fine.
Now that we created the transformation matrices, we should pass them to our shaders. First, let's declare the transformation matrices as uniforms in the vertex shader and multiply them with the vertex coordinates.
Model view projection. How do we pass model view projection matrices in FGFX? Oh, it's not FGFX. What is it? BGFX. BGFX. I never been good at writing. Writing is
How do we
still
pass
the
model,
struggle.
view, and projection matrices in BGFX?
Set view transform. accessing them in shader. Include BGFX shader. Is there
Is
any
there any
new
project you would like to make with your new 3D graphs knowledge?
any graphic knowledge? I would like to make some pet project. Then I learn graphics. I would like to make the Infinite Runner game just to solidify my knowledge, and then based on outcome, I would decide what I would do with my with what I learned. View model, view project. Minecraft clone. Yeah, I want to make not even clone, but Minecraft killer game. But the scope is crazy big. So I wanted to make one instance massive multiplayer Minecraft clone with proximity voice chat. Yeah, anyways. I don't think I will. I do you remember I was making the Mika Craft game? Then I renamed it to Napier. It's probably there is some YouTube videos demoing it. Racing. No. No. Search. Maybe I can do it in studio. Content. Search across the channel. Racing. Oh, here we go. Hello everybody, I leveled up a little bit. Hello. So it was multiplayer game. You can see this is to my other players. So the game is controlled, and people can come and press on the registration button. For example, Mika 2 pressed on the registration button, and button says Mika 2, thank you for registration, and you can see it will appear on the leaderboard here. And I'll do it the same thing from Mika 1. Mika 1, thank you for registration. Again, it's appeared on the leaderboard, and you can see it from our clients also. So let me point to the leaderboard. Yeah, you remember that project, yeah? And this one, so you will see. Oh, it's yeah, private. Oh, interesting. Also. So Mika 5 years ago. And let me do from Mika start a race. Oh wait, let me point so could have a good angle. So you can see here traffic light also. And let me do from Mika start a race, and you can see timer started and traffic light also start moving, and you have to race and click on checkpoints. This is the checkpoints, so you can click on them. You checked, and also you can see Mika checkpoints become 2 and timer is still going. So you have to go to 0 checkpoints to win the race. So it's become 1, and at the end of the maze there is a last checkpoint, and timer stopped for Mika, and I can do same thing for Mika 2. So checkpoint. Yep. So this is the thing. It was made in Unreal Engine though, so okay, so let's go back to AI and set transform. So model view projection, view and projection, set view transform and model. So it's from the shader. Okay, so let's see if we have this call. So just to make sure AI is not hallucinated. BGFX. Oh yeah, so there is a plenty of that. Metaballs, for example, right? View transform. There is a set view rect also. Okay. Set view rect, and what it says, set transform, set, and there is a set transform, set model matrix for rendering. Okay, and in the shader, so we need vertex shader, U model view projection, and U model. Okay, so let's go back to the book. Be right back. model view projection. Okay, so we're just multiplying all this stuff. Let's see. What is it? Coordinate system. And so we've got model view projection. So we can do metables set view set view transform view projection bgfx set view transform view projection. I think I should do it this way. Yeah. Set view transform. And what I said? Model, set model. Oh, just set transform. bgfx set transform 0 model. Set transform. For some reason there is 0 is not needed. Confusion. And let's go to the coordinate system, vertex shader. So let's remove all this stuff. And we would do position. Interesting. Where is the transform? Oh, U model. Oh. U model view projection. U model view projection. Something like this. I think we're good to go. Of course it's crashed. Undefined variable U model view projection. bgfx shader. uniform. Config max bonds, interesting. So this is array. View. Model view. Config max bonds 1, huh? So like this I think should work. Let's see, let's try again. And we've got nothing. We love nothing. So there is a something. Let's start adding one by one. Model view. Okay. It is actually model view. Oh, it's everything. Okay, model view projection. It's everything, so it is tilted. So let me see. Coordinate system.cpp. So if I comment out rotation, so if I comment out rotation here, ah, 800 by 600, but we should do it width by height. So hopefully it would be square. It is squared. Now let's get back rotation. Oh my goodness. Look at this. We are making progress. Projection view model. I am wondering. There is a projection, view, and model, right? Model view projection. So if I do u model times u view times u projection model view projection oh, it's just a proj. Would I get the same result? I've got the same result. Whoa. Whoa.
We should also send the matrices to the shader. This is usually done each frame since transformation matrices tend to change a lot. Now that our vertex coordinates are transformed via the model, view, and projection matrix, the final object should be tilted backwards to the floor, a bit farther away from us. Be displayed with perspective. It should get smaller the further its vertices are. Let's check if the result actually does fulfill these requirements. It does indeed look like the plane is a 3D plane that's resting at some imaginary floor. If you're not getting the same result, compare your code with the complete source code at /src/1. Getting started /6.1 coordinate system / More 3Ds so far. We've been working with a 2D plane, even in 3D space. So let's take the adventurous route and extend our 2D plane to a 3D cube. To render a cube, we need a total of 36 vertices, 6 faces, 2 triangles, 3 vertices each. 36 vertices are a lot to sum up, but let's list them here anyways.
Okay. Vertices of the cube. We are going to make the cube. Coordinate system. So we will remove the color from the cube. So let's do step by step, because I kind of bit burned with like moving fast and things are being broken. So let's move slow. Shader, now we need to fix the shader. Coordinate system, vertex shader, a position, so a text coord 0. So there is a no v color, coordinate system, fragment shader, no v color. Colors are, I do not know if colors are good. Oh yeah, it's yellow. Okay, now let's go back to coordinate system CPP and we are going to copy paste all this stuff if we can. Oh man. Copy. Paste. Pose vertex. Okay. No, it's fine. They did not give a index array. Anyways, it should do something. So there is a 4 vertices per side, right? So this is the bottom one. We see nothing. I'm wondering if I swap these things 1, 2, 2, 3, maybe we would see something. Oh, we do. Anyways, +4, +4, +4, +4, +4, +4. +4 times 0 times 1 2 3 4 oh darn 4 5. Interesting. This is the essence of the 3D graphics. You are getting nothing or mess, and there is no way to debug it. So I think they just screw me up. Because there is no indices. Where give the indices. Oh, you know what I can do? Right there, right Z, dev test, cool, GSTF, cool. So, maybe I can disable cooling at all. Back face cooling mode. So cooling mode. Cool state. Then cool state is not specified. Cooling will be disabled. Let me disable it so at least I would be able to debug stuff. Is there is any I don't want to do it, but I think there is only way to do it. Just do by myself. Do yourself. Blender. Hey, look at this. We do have cube. Okay, so so let me have a triangle first, and let's have triangle from 0 0 0 0 from 0, and let's move it up. And then let's move it on X. Something like this. So now our vertex shader would be 0 1 2. So we will have 3 here. We have a progress. WTF, it's not working. It is working. What is going on? Now it's working. WTF. Exactly. So, apparently, the coordinate system is correct here. So this is Z, this is X. That's good. Oh, we did rotation, right? So did I comment it out rotation? So let's uncomment it. Huh? -55 minus. Minus 6. Okay. So, okay. So they did not lie to us. So let's make comment this thing out. So y is stop. So this y. Okay, let's see. But x is same. Yeah. So this is y. This is x. At least it is right hand system, so should be not too bad. All right. So we are looking at the stuff like this. So let's do this part. So it's let me add the grease pencil. So this is minus plus 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 minus plus and minus minus plus. and we do clockwise. So let's make comment with bgfx. Oh, let me keep it. Let me keep it first. So we want to see if it's drawing something. Minus, 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 plus, 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 minus, plus, minus, minus, plus, minus, minus, plus, 0.5f. Um, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1. Okay, and we want to draw them 0, 1, 2, 0, 2, 3. 0, 1, 2, 0, 2, 3. Let's see. Six. Zero, zero, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1. Okay. Um, okay, so minus, minus, plus. So minus is in the middle. Plus, plus, minus, 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 plus, minus, minus, plus, at least UV coordinates I don't need to do, so that's good. Minus, minus, plus, plus, minus, plus, plus, minus, plus, plus, minus, minus, plus, minus, 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 and B just duplicate. We do 4 times 0, Na, 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 na. Na, na. Na. And times 2. And let's enable rotation. Let's do rotation in the positive direction. So let's see. So rotation is too slow. Let's make it a bit faster. 2 times faster. It's still slow. 5 times faster. Okay. Okay, let's do this thing. So I think we should put CCV. Yeah. So we need way faster 10, 10, and let's do rotation in negative direction. Yay. Okay. So now let's go to that one. So x plus minus y is plus minus and z is minus. Okay. Minus plus minus minus plus minus plus minus plus minus plus minus 2 3 Perfect. And now we would do plus minus plus minus plus 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 minus minus. Plus 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 minus plus plus minus plus plus minus plus minus, minus plus minus, plus plus minus, plus plus minus, should be upside down. Upside down. Yes. Oh, my web camera frozen again. Okay. So let's do this one. So x is minus, 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 minus. Y is plus, minus, plus, minus. And z plus, plus, minus, minus. Minus, plus, plus. Minus, plus, plus. Minus, minus, plus. Minus, minus, minus. Minus, plus, minus. Minus, plus, minus. Ooh. No, I don't want it like this. Whatever. Four, 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 5. So we would not be able to see. Also 10, rotation 10 is too slow. Let's do 20. And we would not be able to see because we are rotating around x. So we want to rotate around y. So let's do rotation around y. Okay. So now we would rotate this direction because so that this marking do not make any sense. So let me delete so I would not be confused. Plus, 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 minus, plus, minus, plus, 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 minus, minus, plus, minus, plus, minus, plus, 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 minus, minus, plus, minus, minus, plus, plus, minus, plus, plus, minus, plus, minus, 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 and 5 5 5 5 5 5 6. Yes, that's it. We have a cube finally. Took forever. Let's rotate it like this, and then rotate around X maybe like this, but like a way slower. Progress, making progress. We are making progress. Okay, so in my case, ZBuffer is already enabled, so it was drawing properly. So I should disable depth test, and it should break the stuff. Oh, it's still drawing things properly because culling is enabled, so I need to disable culling as well. Cooling, I don't know how to pronounce it.
BGFX state cull CCW.
Calling. So let's disable it as well. Hey. Right. Oh, trippy. Okay, be right back. Okie dokie. we are making progress. Actually, we are making faster progress than in the beginning. Even beginning concepts was way easier. I guess I'm just building intuition of all these pitfalls.
It does resemble a cube slightly, but something's off. Some sides of the cubes are being drawn over other sides of the cube. This happens because when OpenGL draws your cube triangle by triangle, fragment by fragment, it will overwrite any pixel color that may have already been drawn there before. Since OpenGL gives no guarantee on the order of triangles rendered within the same draw call, some triangles are drawn on top of each other, even though one should clearly be in front of the other. Luckily, OpenGL stores depth information in a buffer called the Z-buffer that allows OpenGL to decide when to draw over a pixel and when not to. Using the Z-buffer, we can configure OpenGL to do depth testing. OpenGL stores all its depth information in a Z-buffer, also known as a depth buffer. GLFW automatically creates such a buffer for you, just like it has a color buffer that stores the colors of the output image. The depth is stored within each fragment as the fragment's Z value, and whenever the fragment wants to output its color, OpenGL compares its depth values with the Z-buffer. If the current fragment is behind the other fragment, it is discarded, otherwise overwritten. This process is called depth testing and is done automatically by OpenGL. However, if we want to make sure OpenGL actually performs the depth testing, we first need to tell OpenGL we want to enable depth testing. It is disabled by default. We can enable depth testing using GL-enable. The GL-enable and GL-disable functions allow us to enable /disable certain functionality in OpenGL. That functionality is then enabled /disabled until another call is made to disable /enable it. Right now, we want to enable depth testing by enabling GL depth test. Since we're using a depth buffer, we also want to clear the depth buffer before each render iteration, otherwise the depth information of the previous frame stays in the buffer. Just like clearing the color buffer, we can clear the depth buffer by specifying the depth buffer bit bit in the GL clear function.
Interesting. I don't think we do. Let's see. So it's in the main, right? Example update. Update. Viewport transfer. Where's the clearing? That's interesting. There is definitely clearing somewhere. Oh, it's here. Set view clear. Interesting. It is in a constructor for some reason. I would expect this to be in the update. Huh. That's so interesting. So there is interesting consequences, right? So if we enable depth testing, and comment out this part, yeah. So at some point it would not draw anything. Because it's rotating, so it's yeah. But yeah, at some point it should just completely disappear because depth buffer is not clearing out. Cool. So I do understand something. Okay, so we figured out with depth buffer. More cubes.
More cubes. Say we wanted to display 10 of our cubes on screen. Each cube will look the same, but will only differ in where it's located in the world with each a different rotation. The graphical layout of the cube is already defined, so we don't have to change our buffers or attribute arrays when rendering more objects. The only thing we have to change for each object is its model matrix, where we transform the cubes into the world. First, let's define a translation vector for each cube that specifies its position in world space. We'll define 10 cube positions in a glm:\vec3 array.
Cube positions. So I assume we would do we can do this. I guess we can do cube position as stat array, and it's auto, and it's 4. We do it this way, I assume. And yeah, we are iterating, and then we are setting based on the cube position. Cube position. Are we setting model anywhere? Oh yeah, and we are rotating it. Okay, so they're all going to rotate in sync. Ooh. Because we should do angle. Oh, angle is not used, right? Do we have zip? Stat zip. Stat zip. Stat ranges zip view. Ranges include ranges. Stat ranges views zip. X, Y, Z. Okay. Where is it? Where is it? Views zip. Views zip. No member name zip and namespace ranges views. Stat views in namespace ranges views. There is no zip. 2023. And what version am I using? Oh, 20 only. Ah, there is no zip. I want C++ 23. I'm just wondering if it would compile with 2023. Let me try. Just out of curiosity. Working draft for 2023. So if I do 2B. Ah. Shall I switch to 2B? Just to get zips? I need to do sudo deploy. Yeah. Now we have to be. Simple range. Not range. Not range. Size range view. Output range forward range but in random access continuous range. Range has a viewable constant range. Single view, it contains single element of specified continuous sequence generated by a periodic. Oh, iota view, yeah. Iota view. stat views, I guess I need this one 0. And we would need here like this. Expected like this. Maybe it's a stat range iota view. Oh man. Times I. Let's ask AI. C++23, why this is not compiling? Oh, I can do enumerate, views enumerate. Okay, so instead of zip, I can do what am I saying? Stat views enumerate. Stat views enumerate. Enumerate. It's hallucinated. Ranges stat stat ranges enumerate view. What is V? A, B, C, D. Stat views enumerate. No member name enumerate in namespace. Stat ranges view. Include ranges. I'm giving up. I do it normal way. I equals 0, I plus plus. Okay. Let's do more stuff. Exercise. Try experiment with FOV and aspect ratio. See if you can figure out how this affect perspective. Play with the view matrix by translating several directions. Try to make every third continuously the first rotate over time. I already made them rotate. Let's look at FOV. So it's like view translate, view transform, view projection, perspective. So let's do 90 degrees. Okay. $60. It's pretty cool. So next chapter is camera. Coordinate system.
Coordinate system.
It's surprisingly very little changes, right? Huh. It's quite cool. You know what I want? I want probably to rename it for now. Let's call it learning 3D graphics.
Learning 3D graphics.
Okay, and the reason why I rename okay, add this thing to git ignore. Oh, come on. Okay.
Rename the project to Learning 3D Graphics.
Okay, now let's make the public repository GitHub plus new. No. Where's the new repository?
Rename the project to Learning 3D Graphics.
Learning 3D graphics.
Learning 3D Graphist.
Graphics.
Learning 3D Graphics.
Choose visibility public. No readme, no git ignore, no license. Create repository. SSH. Copy. Add the remote name origin URL push. Refresh. Here we go. We've got a project that does not have license yet. Okay, let's continue. I guess I'll go for one more chapter. Combination. And we will call it a day.
In the previous chapter, we discussed the view matrix and how we can use the view matrix to move around the scene. We moved backwards a little. OpenGL by itself is not familiar with the concept of a camera, but we can try to simulate one by moving all objects in the scene in the reverse direction, giving the illusion that we are moving. In this chapter, we'll discuss how we can set up a camera in OpenGL. We will discuss a fly-style camera that allows you to freely move around in a 3D scene. We'll also discuss keyboard and mouse input and finish with a custom camera class. Camera/view space. When we're talking about camera/view space, we're talking about all the vertex coordinates as seen from the camera's perspective as the origin of the scene. The view matrix transforms all the world coordinates into view coordinates that are relative to the camera's position and direction. To define a camera, we need its position in world space, the direction it's looking at, a vector pointing to the right, and a vector pointing upwards from the camera. A careful reader may notice that we're actually going to create a coordinate system with 3 perpendicular unit axes with the camera's position as the origin.
One more thing. The coordinate system. Perspective. I'm just wondering if it looks like I'm going to fight with the system. Why this system is... Why? I mean, it's a OpenGL system, I guess, right? Why is up? So there isn't nothing like a I guess this is the thing what is doing stuff. So I think it's what GLM is doing. GLM perspective. Anyways, maybe I don't know. I really want to do my way and have Z up. And the reason is because in Blender Z is up. So and I agree with Blender. Oh, what is this? It should be Z up, like in Blender. Anyways, we will figure out it later. So let's continue reading.
Camera position, getting the camera position is easy. The camera position is a vector in world space that points to the camera's position. We set the camera at the same position we've set the camera in the previous chapter. Don't forget that the positive z-axis is going through your screen towards you, so if we want the camera to move backwards, we move along the positive z-axis. Two, camera direction. The next vector required is the camera's direction, for example, at what direction it is pointing at. For now, we let the camera point to the origin of our scene, 0, 0, 0. Remember that if we subtract two vectors from each other, we get a vector that's the difference of these two vectors. Subtracting the camera position vector from the scene's origin vector thus results in the direction vector we want. For view matrix's coordinate system, we want its z-axis to be positive, and because by convention in OpenGL, the camera points toward the negative z-axis, we want to negate the direction vector. If we switch the subtraction order around, we now get a vector pointing toward the camera's positive z-axis. The name direction vector is not the best chosen name, since it is actually pointing in the reverse direction of what it is targeting.
Camera position minus camera target. Yeah. Camera direction.
Three, right axis. The next vector that we need is a right vector that represents the positive x-axis of the camera space. To get the right vector, we use a little trick by first specifying an up vector that points upwards in world space. Then we do a cross product on the up vector and the direction vector from step 2. Since the result of a cross product is a vector perpendicular to both vectors, we will get a vector that points in the positive x-axis direction. If we would switch the cross product order, we get a vector that points in the negative x-axis. 4, up axis. Now that we have both the x-axis vector and the z-axis vector, retrieving the vector that points to the camera's positive y-axis is relatively easy. We take the cross product of the right and direction vector. With the help of the cross product and a few tricks, we were able to create all the vectors that form the view/camera space. For the more mathematically inclined readers, this process is known as the Gram-Schmidt process, 1 in linear algebra. Using these camera vectors, we can now create a look-at matrix that proves very useful for creating a camera. Look at a great thing about matrices is that if you define a coordinate space using 3 perpendicular or nonlinear axes, you can create a matrix with those 3 axes plus a translation vector, and you can transform any vector to that coordinate space by multiplying it with this matrix. This is exactly what the look-at matrix does, and now that we have 3 perpendicular axes and a position vector to define the camera space, we can create our own look-at matrix. where r is the right vector, u is the up vector, d is the direction vector, and p is the camera's position vector. Note that the rotation left matrix and translation right matrix parts are inverted, transposed, and negated respectively, since we want to rotate and translate the world in the opposite direction of where we want the camera to move. Using this look at matrix as our view matrix effectively transforms all the world coordinate to the view space we just defined. The look at matrix then does exactly what it says. It creates a view matrix that looks at a given target. Luckily for us, GLM already does all this work for us. We only have to specify a camera position, a target position, and a vector that represents the up vector in world space, the up vector we use for calculating the right vector. GLM then creates the look at matrix that we can use as our view matrix.
Okay. So let's create... What the name of the chapter? Camera. Okay. So now look at view. Oh, same result. Nice.
The GLM look at function requires a position, target, and up vector respectively. This example creates a view matrix that is the same as the one we created in the previous chapter. Before delving into user input, let's get a little funky first by rotating the camera around our scene. We keep the target of the scene at 0, 0, 0. We use a little bit of trigonometry to create an X and Z coordinate each frame that represents a point on a circle, and we'll use these for our camera position. By recalculating the X and Y coordinate over time, we're traversing all the points in a circle, and thus the camera rotates around the scene. We enlarge the circle by a predefined radius and create a new view matrix each frame using glfw get time function.
Uh, 6. Is it right? Oh, there is a outliers 12, 15. But oh yeah, oh my god. Um, what if so? Look at, right, and there is a up vector, and if I say up vector is this one, okay, and look at CAMZ. It's not CAMZ, it's a CAM-Y now. So it's going to become Y 0. Would it work? Ta-da! So let me make it to look at minus 7.5. Yes. And then let me move it back more. So radius 10, let's do radius 20. Yes. Now my brain is not hurting because it shows what my brain thinks. So I can use look at function and say like what is z, where is the up, so z is up. You cannot see, so z is up, and now it's and here's it, like we can see out shooting cubes in negative z, and we can see it's in negative z. Cool, 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 cool.
With this little snippet of code, the camera now circles around the scene over time. Feel free to experiment with the radius and position/direction parameters. Get the feel of how this look at matrix works. Also, check the source code at /src/1.getting-started/7.1 camera circle/ if you're stuck. Walk around swinging the camera around a scene is fun, but it's more fun to do all the movement ourselves. First, we need to set up a camera system, so it is useful to define some camera variables at the top of our program. First, we set the camera position to the previously defined camera pos. The direction is the current position plus the direction vector we just defined. This ensures that however we move, the camera keeps looking at the target direction. Let's play a bit with these variables by updating the camera pos vector when we press some keys. We already defined a process input function to manage GLFW keyboard input, so let's add a few extra key commands. Whenever we press one of the WASD keys, the camera's position is updated accordingly. If we want to move forward or backwards, we add or subtract the direction vector from the position vector scaled by some speed value. If we want to move sideways, we do a cross product to create a right vector, and we move along the right vector accordingly. This creates the familiar strafe effect when using the camera. Movement speed. Currently, we used a constant value for movement speed when walking around. In theory, this seems fine, but in practice, people's machines have different processing powers, and the result of that is that some people are able to render much more frames than others each second. Whenever a user renders more frames than another user, he also calls process input more often. The result is that some people move really fast and some really slow depending on their setup. When shipping your application, you want to make sure it runs the same on all kinds of hardware. Graphics applications and games usually keep track of a delta time variable that stores the time it took to render the last frame. We then multiply all velocities with this delta time value. The result is that when we have a large delta time in a frame, meaning that the last frame took longer 10.5 look around 99 than average, the velocity for that frame will also be a bit higher to balance it all out. When using this approach, it does not matter if you have a very fast or slow PC. The velocity of the camera will be balanced out accordingly, so each user will have the same experience. To calculate the delta time value, we keep track of two global variables. Look around only using the keyboard keys. To move around isn't that interesting, especially since we can't turn around, making the movement rather restricted. That's where the mouse comes in. To look around the scene, we have to change the camera front vector based on the input of the mouse. However, changing the direction vector based on mouse rotations is a little complicated 100/10 camera and requires some trigonometry. If you do not understand the trigonometry, don't worry, you can just skip to the code sections and paste them in your code. You can always come back later if you want to know more. Euler angles are three values that can represent any rotation in 3D, defined by Leonhard Euler somewhere in the 1700. There are three Euler angles: pitch, yaw, and roll. The following image gives them a visual meaning. The pitch is the angle that depicts how much we're looking up or down, as seen in the first image. The second image shows the yaw value, which represents the magnitude we're looking to the left or to the right. The roll represents how much we roll, as mostly used in spaceflight cameras. Each of the Euler angles are represented by a single value, and with the combination of all three of them, we can calculate any rotation vector in 3D. For our camera system, we only care about the yaw and pitch values, so we won't discuss the roll value here. Given a pitch and a yaw value, we can convert them into a 3D vector that represents a new direction vector. The process of converting yaw and pitch values to a direction vector requires a bit of trigonometry, and we start with a basic case. Let's start with a bit of a refresher and check the general right triangle case with one side at a 90-degree angle.
Anyways, this is simple trigonometry, nothing special. Mouse input. So mouse input. Zoom, little extra camera settings. We also implement the zooming interface. We can do it with field of view. Okay, I don't need tutorial, I can implement it by myself. This is a basic trigonometry. So we would have extra functions which would do let's do strafe maybe. Float dx, float dy.
Autostrafe float dx, float die void.
Strafe. Is it like correct? I forgot the name. Strafing. Strafing is a maneuver which involves moving control character or entirely sideways relative to the direction it's facing. Okay. Dx dy. Forward, right, auto look, float dx, float dy. Wait. So we need GLM, glm vec free camera position, glm vec free camera I guess we just need camera. Oh, we can do float camera yaw, float camera I forgot the name. Yaw pitch. So camera position would be glm avec free 0 free 0, and camera yaw and pitch would be 0 and 0. Okay, so now come. So let's get rid of all this stuff. Come y come. So it's going to be. I like contraction. Let's contract it to come yaw, come pitch. So it's gonna be come pause, and so pitch and yaw, pitch and yaw. So we have a vector and this is I guess this direction is yaw, and this direction is pitch. Right. So first we need to do pitch rotation and then we do yaw rotation. So we do a pitch rotation. So we have initial vector temp vector vec3, which would be 1 0 0, and then GLM. We need to GLM rotate GLM mod 4 times and GLM. I don't think I should convert to radian, so I just take the so we do pitch first. So come pitch. So we do pitch first around y-axis. So GLM vec3 0 1 0. I guess I need vec4. Yeah, and then we do another rotation, which would be yaw around z-axis. And we plop it here. That's it. Call look at what? Why? No matching function, not candidate template, ignored, could not match. 3 against 4. Vector center up. Oh. Okay, something is happening. Oh yeah, now we need to implement strafe and look. Not sleepy, honestly. No. So strafe and look. So let's do forward compose plus equal vec free and plus equal. I guess I would do no, not hungry. So moving forward, so we need to do this thing. And then const auto at equals that times forward. Yeah, let's keep only forward, and that thing come your plus equal dx come what is this? What the name of this thing? Pitch plus dy. Okay. Main. So key down. I guess I should do yes, I need to do switch here. Switch and case done equal true. Break. And we should have variables forward to false, backward, false. So let's implement this thing. Case HDL Okay, w forward equals true, break s backward equals true, break, and we need to implement up as well, up, and it would be false, false, and example dot starif 0 here, and forward 1 0 plus backward 0 minus 1 0. Doesn't do anything. Camera. Oh yeah. Okay, so we can move forward and backward. Now we need to do mouse move equals const sdl mouse event sdl mouse event mouse motion event, mouse motion event, xrel yrel, xrel yrel. What's going on? Auto mouse dx equals 0, to mouse dy equals 0, and mouse dx equals e dot rel x, mouse dy equals e rel y. Mouse not found. Xrel, Xrel yrel. Example look xrel y Arial. Mouse dx, mouse dy. Oh, mouse dx equals 0, mouse dy equals 0. Should be inverted, right? What's going on here? It's doing some weird like huh. Camera. Stats out. I can do log include log.hpp log cam yo pitch cam pitch. Here this is the bug. Ah. Let me keep only yo so I would understand what's going on here. Yeah, it does work. You just invert it. So yaw is working. Now pitch. I think pitch is also working. It's just super sensitive. Let me change the minus here maybe. It's broken now. I do not understand why. I think I have to clamp pitch, right? If clamp pitch less than divide by 2, I guess stead max stead oh no pitch equals clamp pitch So we clamped pitch. Uh, it's still very sensitive. Maybe. Oh, that's better. Let me do the style mouse to mouse down equals false, and let's do mouse button down mouse button event, and mouse down equals true, mouse up mouse down equals false. And if mouse down. So let's now implement forward, backward, auto left equal false, auto right equal false. A D right left left right false false right left. Let's ask AI for help. Actually, at forward And right. It's still very touchy. So let me. Where is it? Also, forward and backward. I guess we can do it here. Yeah, we can do it like 0.2. Yeah, some sort of camera movement is implemented. I told you I can implement it by myself. Uh, Let me ask AI, do we have a better way to get vec 3 from vec 4? Okay, so we can do like this. Would it work? Ah, that's nice. So I guess I should probably do camera position -10. Hmm. -10. Yeah. Cool. Where's the book? Yeah, I'm not going to do zoom. Review.
Congratulations on reaching the end of the Getting Started chapters. By now, you should be able to create a window, create and compile shaders, send vertex data to your shaders via buffer objects or uniforms, draw objects, use textures, understand vectors and matrices, and combine all that knowledge to create a full 3D scene with a camera to play around with. Phew, there's a lot that we learned these last few chapters. Try to play around with what you learned, experiment a bit, or come up with your own ideas and solutions to some of the problems. As soon as you feel you got the hang of all the materials we've discussed, it's time to move on to the lighting chapters.
Hey, we are getting lightning chapters. Okay. So all of this thing had nothing to do with 3D. I mean, it's had, but it's not like sort of rendering theory, just figuring out how to use API. Oh yeah, camera. Okay, I'm done for today and hopefully see you next time. Bye.